and go on, and there, we got sound for the live stream. Yeah, seems like we do. So we had two explanations for trends that I'm going to revisit and hammer over and over and over again for the next one, and then I'm going to have you do that. First trend is you go down the table, you're adding more shells. The magic word that tells you that that the atom's getting bigger, or the attraction of the outer electrons are less attracted to the inside, is what? Oh, hold it. We have a new student. I have to add them. Okay, there we go. Oh, darn. I added them to the wrong class. Added students. Kate. So I'm going to ask Jacob. Well done. What is the name for the process by which these outer electrons feel less force from the nucleus as you go down a family? The shielding effect. Because you are adding more shields. Shields up as you go down. As you go across, as I explained last day, the atom is getting smaller. Because what force is acting as you go across? Let's Martin. What I'm pointing at.
Yeah, I forgot my contacts at my house during Thanksgiving break.
Oh, okay, you've been sitting there and not been able to see the whole time? How are you taking notes? That's insane. No, stop. Would it help if you sat up here? We did this, I remember. Okay, for you, open a second tab and join the live stream, because at least you'll be able to see the notes. Okay? Yeah, well, that's as you saw before, which you can't see. Go to YouTube, search for Juan Newton. I'm so famous that I should be like the first one that comes up. That's the one. And it says live now. There you go.
I can see.
Okay, so what's happening as you go across? Look at that little number up in the corner.
The number is increasing.
Right, and what does that number represent?
Protons.
The protons. So the protons are increasing. So what's happening to the attraction to the electron? It is increasing. Excellent. So those are the two explanations we did last day. This was the increasing protons. Now, whoops. Let me get out reference. No, don't put on the sound. That'll throw me right off. I don't know about you, but I hate the sound of my own voice. Oh, yeah, it's definitely got like a few second delay. Okay. Oh, next thing I should make sure we do. We have a quiz. Next week, Thursday or Friday, it's going to have like the state diagram, solid, liquid, and gas, pure versus mixture, isotope. Today is Friday, which means our quiz would then probably be on Thursday. Yes, question? No. Test is probably the week after. So quiz next week, possibly test the week after or the week after that, depending. Depends when we're done quantum. But I want to see something with calculations on it. What kind of calculator do you have to come to class with? Scientific calculator. If you come in with a graphing calculator, will I let you use it? No. Long division by hand. Pardon? Your graphing calculator? No, you're probably cheating. It should, But I don't know what you're doing on a graph. You can program a graphing calculator with programs that can think for you. Now, if you're the one who programmed it, I'd actually consider letting you do it. I had a student in grade 11. He programmed his calculator. This is years ago. So he could put in an equation. You know the hard math stuff I warned you about? It would do all of it for him. He put in a chemical equation. He put in what data he had, the number of moles, grams if needed, and then it would just calculate everything. Just everything. And then he'd pull up the number. Now, for him, that was brilliant. He had to understand it in order to do that, so no problem. But except he gave it to all of his friends who had no idea why it worked. It just worked. We caught him, not caught him, but I found out from the other ones because he actually had an error in his programming, so there was a consistent mistake. He knew to adjust for the mistake, but nobody else did. And so when everybody came up with exactly the same wrong answer, it looked like everybody was copying off of each other. Yeah. Yes?
So if I did that, I'd be allowed to?
If you program it and can go through the programming, I might consider it. Yep. It should say scientific. How I tell a scientific calculator if it's difficult is I look to see if it has a log function. All scientific calculators have a log functions, and the other type you can buy that look complicated are often accounting calculators, and they never calculate logs because they're wimpy. No, if it has a log function as a scientific calculation, you're good. If it is a graphing calculator, it has a big screen and you can draw graphs on it, you're not allowed to use that. Yeah. So here, example. You are not allowed to use this calculator. And you should not use it for your homework. Because you should use the calculator you're going to use for your quiz and your test that you're at home as well as here. Because in the middle of a test, you don't want to be able to do, how do I do scientific notation in my regular calculator again? Or this is the first time I'm using it. That's a bad time. So you're not allowed to use that. A scientific calculator costs like, you can get them on, I just saw them on sale in September for like $8. They're probably not on sale anymore at Staples. The student store probably charges you, I don't know, like $250. Normal markup for the school store, but you could order one off of Amazon if you need. A scientific calculator, do we have scientific? That was a scientific calculator. So that one, right on it, it doesn't say scientific, it says a lot of things, but it has a 10 to the x. It doesn't have, and it has a log function, so this will work.
That's what I need. Perfect.
Nice. That even has your name on it. EE, so you have the scientific. Not seeing log. Oh yeah, you got that's good. Yeah. Yeah. So I want to start this. I'm not going to go and check everybody's calculator. But if you're I will check it on the day of the quiz or come to the tutorial or in between classes and I'll check it out. Does everybody have this down for what's on your upcoming quiz? Protons, neutrons, electrons. No. If I have copper, how many protons does it have? What's its atomic number? And I'm going to say it has 27 electrons. What's its charge? So remember that table that you've done where you've like filled in all the different subatomic particles, protons, neutrons, electrons? Like that sort of thing. Are you familiar with the Bohr model? If you know that it has 29 protons, then and 27 electrons, what's the charge? Yes? 2. Excellent. So that sort of thing. Yes? No. You will get completely fresh periodic tables. So the periodic tables you have are your own personal ones where you write things on because that's like, I need to know that. But the ones you get for quizzes or tests are the exact same one, but they're fresh. They are unwritten on or written on by someone else, so you don't know if it's right or not. Because we do reuse them. Yes. What we're doing right now. Yeah. 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 That stuff. Okay, good. Everybody got that written down? Excellent. So, to review from last day, using these two effects, shielding the increasing number of protons to summarize the trend in atomic radii, draw a periodic table. Write this down, draw a periodic table. Look at that beautiful periodic table. It's getting there. It's getting there. Shh. Josh, I don't remember you being this sarcastic last year. You changed, man. You went to what? Okay. First off, going back to, who? What?
We need like a full page for that, and like the whole detail.
1 second. This just, okay. It says it's already added to class, but where's your name? There it is. Okay, I'm going to pick, actually not randomly, but people who need more points. We're mostly at 3 or 4 points. So, Alexander, bringing you up to 4. What happens to, now you can answer either up and down a family or across. What is the trend in atomic size? It increases if it goes to the right. Goes across, so this way. Oops. So I'm going to go back to this trend. What happens as you go across the periodic table in terms of the charge? It goes up. What happens to the attraction to the outermost electrons when it goes up? Increases. What will that do to the size as you increase the attraction? Make it smaller. So radii, which is the fancy word for atomic size.
That's the actual reason, or just because
That's the actual reason. I mean, really, I could say either one of those and you won't know the difference. So, but it is. I mean, the atomic, it's a fundamental physical force. The attraction is increasing, so it's going to pull it closer together. Atomic size. Yeah. Like a radius of a circle. So I wanted to use that terminology because often it'll get phrased that way. Now, someone else who needs points.
Did you write down atomic radii increases?
Yes.
As plural and the S and the N of the verb?
Oh, that's easy to answer. I'm not an English teacher, so I do what I want. Next one. No, I said it right here.
Yeah, no,
But we corrected that.
S and the N.
No. It decrease. And why does it decrease, Jonathan? What is happening to the amount positive charge as you go across? And what is happening to the attraction on the electrons as that increases? Increasing a positive charge towards a negative charge, the attraction would increase. Remember our example when we stood up in the front of the class and you had more and more protons? Oh, he wasn't here. That was it. Yeah. More protons, more attraction, pulling everything together. Okay? The electrons don't matter as much because they're acting independently of each other. It matters the most about the proton. Yeah, the electrons would be sad if you said they didn't matter at all. So they matter a little. Yeah. Yes. Yeah. Yeah. It's size of the atom. Why? Are there more shells as you go across? And there's more protons. So why? There is more stuff, but there's also more attraction. And most of the atom is empty space. If the nucleus gets bigger, does the atom get bigger? No, because the nucleus is a tiny little part of it. So what really matters is what are the electrons doing? And the electrons have more positive charge attracting them, so they get smaller. No, the volume they're taking up gets smaller. Correcting my English again. So you're asking about down? So when you go down, down is different because what are you adding when you go down? So you go from here to here, what changed? You added a whole new shell. And this shell is repelling the outer electrons because they're negative and negative. So in addition to the extra attraction, you have a much stronger repulsion. And that pops that one out quite a distance. So down bigger, across smaller. Does that make sense? Those were all excellent questions. Atomic radii decreases that way. And it also decreases that way. Now, in addition to that, random Keith. Where? Radii. Plural of radiuses. Oh, sorry, you confused. I don't know. What was the question? What did I ask?
You didn't ask any question. You just said.
I just call the same. Wait, I'm going to think of a question, and you're next. Oh, right. If we take some electrons away, I'll set up the question, then I'll ask you, because that's fair. So remember, we have a staircase line in here. For this side, what do these elements tend to want to do with their outermost electrons? Yeah, this side. Get rid of them. So if we get rid of them, what would you expect the size of the atom to be? Smaller or bigger than its neutral state? Smaller. You got rid of a whole shell. Yeah. So when you have a positive ion, it tends to be smaller. Now on this side, if we add electrons into the same shell, would you expect the atom to be smaller or bigger? Donald? You need to be sitting up, paying attention, not putting your head down. On this side, do the elements tend to add or get rid of electrons? Add. If you add electrons to a neutral atom and you have something with a negative charge, would you expect it to get bigger or smaller? If you add electrons, say you have oxygen, which would be about here, and you make it a -2 ion, would you expect that to get bigger or smaller than its neutral state? Smaller. Why would you expect it to get smaller? Oh, well, I need the reason. Yeah, no, that's not a reason. That's just guessing. Question, Keith? Electrons? They won't react. So they don't react with each other. They'll react with other things. Yeah. So like oxygen and fluorine don't like to react with each other because they're both trying to get rid of electrons. So positive ions we've answered. Smaller than neutral, which makes sense. So since you guessed, Donald, I'll give you another one. What do we call positive ions? They have a fancy term. Other one. Cations. Cations are positive, remember, because they're like a cat and they have paws. Cations are positive. Excellent. Well done. Negative ions. Now, what did you guess again, Donald? Negative ions? You said get bigger or smaller? I can't remember your guess. You don't remember your own guess? Make another guess. Smaller. Now, often people do guess smaller. Does anybody agree? And what would your reason be? Well, they could both be smaller. Yeah? Oh, okay. If they're in the same shell, would you expect it to get bigger? Yes.
I think it would. I would expect it to be bigger because of the probability thing. Since like you have like a space, and the further you go like away from like the middle of the shell, basically,
Yeah.
where
Yeah.
the highest,
Yeah.
the lower the probability gets. And as you get more electrons, the probability that the outer edge of the shell is higher.
Oh.
Usually, like there is the probability of any electron being further out
Yeah.
is higher.
So you're saying
At the
that.
same time, the whole shell has like more negative charge, but it doesn't really care. It doesn't really matter. Also, the electrons repel each other.
Yeah.
Right?
They do.
So they push each other like away. Yeah.
It's that.
I think it's bigger.
The trend is correct. It is bigger, and that is an awesome explanation. It's completely wrong, but it is complex. If it was said on Star Trek, I would believe it instantly because you're using all the right terms in terms of probability. There are effects that use that probability to increase the probability. The atomic size is different than that. What happens, because if your explanation was true, then as you go across, these should also get bigger because you're adding more electrons and you'll be adding more probability.
Yeah, but the protons have a higher impact.
The protons do have a higher impact. So yeah, you could explain your way around it, which is good. What happens is when you get to the end, and by the end I mean when you fill a shell completely, it actually puffs out a bit. At the lowest energy level, the atom, the best way to describe it is that it relaxes. And then they fill up every available space to them. But they don't do that until the shell's completely full. So it isn't like they're doing it all along. They only do it at the very end. Yeah. And so then I say quantum. Bigger with full shells. And that's the only explanation I'm going to give with that. What are negative ions called again, Donald? Anions. Yeah. And then I immediately got up and got in the way. Yeah, I'm moving out. Why do you have a crowd detector? Don't play it. Let's not just see that. I have seen that. Not that one. I'm pretty sure they're going to release Skyrim for it any day. Yeah. Oh, I'm positive. There's probably a Doom. Yeah.
Yeah, it's just literally everything we just wrote down.
Well, when we were adding electrons on the opposite point, it didn't get there. And notice I very carefully often I'm going to the noble gases. That often gets smaller, 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 smaller. And then when you get to you have the noble gas, it actually gets slightly bigger. But when you go across, there's no more cells. Yeah, I know. Add cells to get bigger. It's going to get smaller. Just across the periodic table, there's more protons. But if you just add electrons without actual protons, you fill up the shell completely, then it gets bigger. Yep.
It's not true.
Okay. Looking this way.
Why is there blue and purple?
Oh, I'm going to go over this. So, rather than making you draw this, because this would be silly, I have the, notice I very carefully don't include the noble gases, because we're asking you towards the general trend. And in purple is the regular neutral atom. So you can see that it gets smaller. If we added in the noble gas, which we tend not to do in chemistry 11, because then you get silly questions, is that it actually gets a little bigger again. Because once we fill up a shell, the atom kind of relaxes, and then it fills up all the space, in that it's possible in that shell. However, we see that effect when we have the ion. So this is an N3 minus ion, and it's quite large compared to the neutral one. It's relaxed out quite a bit. But the trend is still the same, and it doesn't matter how many electrons have been taken away. I mean, this is 3, 2, and 1. The biggest one is where we've added the most electrons, added second. But now the trend is still adding more protons makes it get smaller. So you can see the trend is the same even amongst the ions. If you take away the electrons, then of course you're removing an entire shell that is much, much smaller. And as you go across, it gets smaller still, because again, you're adding protons. Yes?
Some don't have I believe that's because
Sorry, what? No, they didn't include it on this trend. It just has a neutral one. The carbon +4 ion or the carbide ion they haven't included. I actually don't know why. I don't know. I just grabbed the table because it looked cool. Yeah.
So I'm just a little confused about how what gets smaller.
So as you go to the right, what's happening to the side?
Gets smaller.
It's getting smaller. So atomic radii are decreasing across the period from left to right. And here, the number of protons attracting the electrons in the same shell. So as we're going across, what's the number of protons here? Right, lithium. 3. What's the number of protons here? 4. So we're increasing the attraction to those electrons. So they're pulling them in more and more. Whereas we go down,
the size of it gets bigger, but the protons get or size of it gets smaller than protons get.
yes, yeah. And as you go down, you're adding more shells,
Like valence shells?
like valence shells. And so they're getting bigger. Atomic rate is increasing because of the magic word, shielding effect. Shields up. As we go down, we're adding more and more layers, more and more shields. Good? Good, good. Yes, Sasha? Oh, that's for the entire table. I am teaching you a general trend. And if you notice, like, anything that is slightly different, like, oh, this one doesn't, like, you find one in here that doesn't correspond, we're ignoring those. I rather suspect that's why carbon's not included, but I can't remember what carbon is exactly, so I can't say that for sure. I mean, they did include this one. Look how tiny. Yeah, they didn't include any of these that have both. Maybe it was just room. Okay. They include there, it is. Oh, reactivity. Draw another periodic table. Yeah. I'm going to draw it too. That's what makes it extra fun. Extra fun. Now, what family doesn't react? Noble gases. So for this particular trend, we're going to take the noble gases and remove them because they don't react and don't do anything useful. They're the 1% of the 1%. They just sit around and force Amazon workers to do everything for them. Bezos. I know, no, don't extend the analogy too far. It just stops. It stops there, and that's it. Okay. Once again, I'm going to include a staircase line. This is a little squished of a periodic table, so I'm just going to. I haven't done that yet. So I'm going to take that as my staircase line. Let's make it purple. We got staircase line. Make that smaller. Put it right there. Color code it so you can see it. It will also be purple. There we go. Nice. Look at that. Look at that color coding there. Now, where's the highest reactivity? I should ask someone who needs point. Kate needs point. Kate, what is the most reactive element on the periodic table? Pardon? The one at the end. Which end? You're pointing to the left, to the right. So here, and top or bottom? Top. What element is that? Pardon? Oh no, if you're going up, there's one more above chlorine. What? Oh, did you say fluorine? Oh, I heard chlorine. My apologies. Yeah, it is fluorine. So with this, the highest reactivity is here. And let's there we go. Oh, that's terrible. I need that nice blue.
What is it most reactive?
There we go. Shh, I'm doing things. There we go. Okay. Sorry? Oh, well, you've just volunteered for the next question. Kate gave us the most reactive element, but unfortunately, she only gave it on one side. It was a trick question. There's two most reactive elements. What's the other one? It is on the left. So it's somewhere over here. A reminder, we threw this trend into the water and watched it explode. Francium. Excellent. No, but we did lithium, sodium, potassium. It would be great if we did. So we have francium. We have francium down here, which also has a highest reactivity. Don't count those for reactivity. Highest reactivity. And let's make it green as well. What is that there? Which means our trends are this way. Highest reactivity and highest reactivity. They differ across the staircase line. But now that we have our explanations, we can use them for this. Once again, on this side of the staircase line, let's ask, on this side of the staircase line, what do these elements want to do with their electrons? Go Holland. Do they want to get more and become negative, or do they want to give them away and become positive? Yeah. So they give away electrons. What are positive ions called? Cations. Give away electrons. These are known as cations. And of course, on this side of the staircase line, Alexander is being called again. That's the nature of random. Oh, hold it. Am I in your way? On this side of the periodic table, do they want to give away electrons or add electrons? On the right-hand side, yeah, right here. They're going to add. So in here, we want to add electrons. What's the name for negative ions? Anions. Excellent. This difference in what they want to do accounts for the change of reactivity. We can explain both trends based on what they want to do. So if you're trying to give away electrons, and we'll take this one first. So I'm going to use down a family. Why does it become more reactive as you go down a family for the metals if they're trying to give away electrons? You've answered a lot, so I'm going to either pick up. You haven't answered one yet. Go. Yeah. Further out. So, what is the magic word that explains why they're further out? Your explanation was perfectly good. I want to re-emphasize the magic word. No. Starts with an S. It's two words actually. The second word is effect. Shh. Tell them. Yes. Shielding effect. As you go down, you increase the number of shields, and so they experience less and less attractive. If you're trying to give something away, then having less attraction helps. If you want to like very casually break up with your significant other in grade 12, just make sure you go to universities that are really far away from each other. Oh, sorry, I'm sorry, I have to go to this university, and then just mysteriously, you'll start dating other people. I'm sorry, it's just chemistry. Yeah. Now the other trend, Martin. The other trend, this way, why does it become more reactive as you go this way along a period? If you're trying to give away electrons. No, you've answered too many. I'm going to ask Kate. Kate's catching up. As you go this way, why is it becoming more reactive if you're trying to give away electrons? You're only your first day in class, so not really fair. However, I'm going to go back to this. Shh, don't interrupt. Shh. If you're going this way, what is happening to the amount of protons? Louder? It's decreasing. So what is happening to the force on the electrons as you go this way? If you're decreasing the amount of positive charge? I'm going this way. So if you're decreasing the amount of protons, what is happening to the attraction to the outermost electrons as you decrease it? It's getting weaker. So if, to go back to this one, if it's getting weaker, then why would francium is trying, as you go this way, they're trying to get rid of electrons. So as you go this way, why would that then make it more reactive? It's the weakest one. As you're going this way, there's a weaker and weaker hold of the electrons, which makes it easier and easier to give away. The exact same trend can be used to explain why the trend is opposite up here. So the explanations work in either case. If these are trying to add electrons, then going, let's pick this way, since we just did it the other way, going that way, why is francium the most reactive element? Go with Anton. If you're going to the right, why is it easier to add electrons? Why are they more reactive? Oh no, you're talking about them wanting to fill up their shell. But I'm talking about the force. So as you go across, what's happening to the attraction to the electrons? There's more, what? There's more protons. There's more protons. More protons means more what to the electrons? More attraction. So francium would have the most attraction to electrons. And if they're trying to pick up electrons, then that helps. Going up, what effect is increasing the reactivity there, Joshua? Going up the family here, why is fluorine the most reactive element? Yes, why is the size decreasing? Well, it's size and this are both related. So you used one effect to explain another effect, but both of them are the same explanation. What effect, magic word, is decreasing as you go up? Shielding effect. If there's less shielding effect, is the attraction to the electrons more or less? More. Less shielding as you go up, more attraction, which means because they're trying to gain electrons, most reactive element. Francium is more, but what is francium trying to do? Give away electrons. Nothing. Well, there's just one electron if it's just neutral francium. It just has to give away that one electron. And it has the most shielding effect and least number of protons. So most shields, least protons, because it's not going across and adding protons. It's all the way over here. We've added all the shells, 2, 8, 8, 18, 18, all the way here. And so that one electron is held by the weakest nucleus it can have. So it's really, it's like, you're here and your girlfriend or boyfriend is over in, I don't know, Spain. You're never going to see them again. Oh, anything that it can wreck. It would just be extremely easy to take it from it. It's like literally a little baby. You just, punch the baby in the face, you take it, there's no resistance. Yeah. Whereas here, the one it could react with the most would be fluorine. Fluorine over here, francium is trying to give away its candy. Fluorine's trying to get it. It has the least shielding effect, so the strongest hold, and the most protons, strongest hold. And so it can grab electrons quite well. So because it's trying to get electrons, that helps it. Good. We're going to do that again. So for the next trick, draw another video on the table. No, don't sigh. It's fun.
Drawing periodic tables is fun. This is fun. It's like when your parents told you had to have mandatory fun. Yeah, mandatory outside time. You have to go outside and have fun. You're like, but it's not fun outside. And they're like, shut up. Go outside and have fun. Oh, well, that's fair. That's true. We can include the school in that. Well, and when I say your parents, like technically the school is your parents. We have in loco parentis over here, which means technically speaking, Mr. Patel is legally in the province of British Columbia allowed to spank you. Oh yeah, you're allowed to spank a child provided it is only with the hand, and basically the wording comes out like not that hard.
So like a cat, like a love cat.
A love tap. Yeah. So like if your parents hit you with a spoon, that's not allowed. They have to like barehand it. Yeah. I think our culture has changed enough that people would still question that, but technically they haven't made it illegal. And I think if Mr. Patel spanked you, there'd be all sorts of other problems going on. Yeah. Yeah. Can you imagine the YouTube broadcast? In This Week at Brentwood, okay, once again, we're going to get rid of the noble gases. And I've defined what electronegativity is below. And just to emphasize it, I'm going to draw a water molecule. And the Lewis structure, if you remember Lewis structures from last year, those are unshared electrons. And those are shared electrons. So electronegativity is the attraction for a shared electron by the nucleus. We don't include the noble gases in this trend because they don't share anything. Again, Jeff Bezos. Pardon? They don't. It's just in the news now. It's a common cultural reference. Yeah. You know, if we were being taught this in the past, I'd probably be like using like King George V. I actually don't know anything about King George V, so I don't even know if that would be relevant. But I'm assuming there is one. Now for this one, I want you to tell me what the trend is based on those two explanations that we've done for across and up and down. And to help you with that, I'm going to put you into groups. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 3 people. Seems good. We are block B. We are group maker. 3 people. Nice. Find your people and go to them. Find your people. Find your people. Go to your people. Go, like physically. Go to your people. Like you need to be in a group. In a second, once everybody's found their people, grab a chair nearby. Go to your people. Yes.
Or notes. I can't write all of them.
I'm putting the screen we're on back up in just a second. Oh, yeah. Right. Email me to give you the notes. Yeah, and I'll post them.
Is it
I forgot about that. Yeah.
in the tutorial or something like catch up? Like, cause I know the lessons like on that, but
I want you to get the notes first and go through the that, and then come see me. Yeah. Okay. Is everybody in their group? Okay. So in your group, make sure that you understand the definition. Use the explanations to come up with a trend. I'm going to ask groups for A, what is the trend, and what is the explanation in either case. and to explain what electronegativity is. So I want you to come up with the trend. We've done the explanation 2 or 3 times. In your group, finish this off. Put in the trend, put in the arrows, and put in the explanation. I like the positivity. I want you to figure out what the trend is. Where's the highest or lowest electronegativity? So there's a trend. Is it highest over here, over here, over here, over here? Does it increase when you go across this way? Does it increase when you go that way? And how does it do it up and down? So knowing it's the attraction for a shared electron, how does shared means it's in a bond? Shared means it's in a bond. No, it's not just atoms. It's now between. So this is a different trend. Pardon? So it's a trend. Like I'm just asking, where's the most electronegative element? In the same way, I could ask you, where's the element that has the highest reactivity? Oh, I'm not telling you. Well, remember your 2 trends. Do we ever pick something in the middle? No, it's not. There's no trick. I want you to take the 2 previous explanations, and it's either going to be top right or bottom left. Yeah. It's 5 minutes. Okay, so Where's the most electronegative element? That's good. Stop, everybody. Okay. If I need to stop, hold on, where's my phone? Stop for a minute. I'll pick a random person and then that group will be on. So elect a spokesperson. So Evan's group. Explain what electronegativity is without just reading that sentence in your own words.
Like the nucleus, right? It holds the electrons because they're negative, and depending electronegativity just tells you how much it holds.
What kind of electrons?
Valence electrons.
Good.
All of them get full, I believe. I would have to guess. I would say all of them get full, but the valence electrons.
Which valence electron for electronegativity matters the most? What is it in? What's that called? No. What's this called? A bond. So electronegativity is always the attraction of electrons in a bond. There's another way of saying unshared. So good. Now for a trend. So that's Ned, your group. So you can now pick the trend. You can either go up, down, or sideways. Which are you going to do? Sideways to the right. No. You only get to do one of them. Which one do you want to do? Sideways to the right. And what is that? No. Is that increasing or decreasing electronegativity? Increasing electronegativity. Oops. Increasing electronegativity. Now, I didn't ask you for the reason because I'm going to ask another group because there's lots of groups. Jonathan, your group. What's the reason for the increasing electronegativity? No, that's not how it works. Sure. Why does the electronegativity increase as you go from left to right?
Because the nucleus gets more positive.
Yeah. What? Yeah. Nice. And that increasing positivity increases the attraction to the
Negative.
Yeah, the shared electrons.
Wait, so were we right that it goes right?
Yeah. I'd like you to confirm that right after the explanation. Well done. Okay. Richard. Where's Richard? There you are, Richard. What is the trend going up and down?
Wait, they haven't answered yet. Why would you say that?
Yeah, no, it's randomly generated. So your group, someone from your group, who's ever the spokesperson.
The electronegativity increases
Upwards. Excellent. Nope. One. Well, I mean, depending on how you parse it. No, you didn't. Lies. No, stop doing that. The Hyundai. Up. Increase. What is the reason for the increasing electronegativity as you go up? It actually gives less protons. More protons is this explanation.
Now you can do it up or down. You can say decreasing electronegativity down or increasing up. But what is the trend when you're going up and down a family? There's a magic phrase. Shielding effect. So as you go up, what's happening to the shielding effect? It's what? Decreasing. You're losing the layers. What happens to the attraction to the electrons when you decrease the number of shields? It gets easier, yeah. Stronger. 1 second. So, no. So as you go up, decreasing shielding effect, increasing electronegativity. So that is the trend for electronegativity. Well, what you're doing there, I mean, the distance does decrease, but the distance decreases because of the shielding effect. So what you're looking at there is a common cause. So when I'm looking for an explanation, I'm not looking for, well, the size is different. I'm looking for why is the size different. So it's the same cause for both of them. Yeah. Everybody go to this? Go back to your seats. Get these notes down. Ned, what are you doing? Does everybody have this down? Get that down. Richard, everything okay?
Yeah.
You definitely what? Okay, Richard, focus on the lesson. Whatever I heard there, it sounded fairly negative. Was it negative? Excuse me, Herr Neufeld. Okay, but we don't want to have that here. Go talk to your house parent. Gentlemen, quiet, please. Okay, so no, I've added a new one. You're drawing a new one. So once you're done electronegativity, we have a whole new trend called ionization energy. Oh, yes. And for ionization energy, if I was to do it with, say, helium, where I have 2 protons, 2 neutrons, and then I have an electron bound, it's the energy required to rip that away. And we include noble gases in this. They're both talking about electrons, and you may notice a correlation, but they are defined differently. And I am once again, no, that's a separate calculation. Yeah, it's measured in a different way, and so it has a different amount of force. You can't. There is no straight calculation you can do to predict it. I mean, you can give a ballpark based on the electronegativity, perhaps, but you're still talking about electrons. But we include the noble gases because we can force an electron away from a noble gas. So, like, you can force Jeff Bezos to pay taxes. How much energy would that cost? A lot. He might have more money than the IRS. No, he's just in the news. And I know his child doesn't go here. So, you know. What? His child does not go here. Yeah. I do remember I was sitting down helping Chemistry 11 with a particular student, and she was just really tired of doing like, can I just bribe you for a better mark? I'm like, sure, what do you got? And she's like, I don't know. And I said, I can't give you money because it'd be too obvious. I'm like, I don't know, free food for life. And she said, how about fried chicken? Apparently, she could arrange that I could have Kentucky Fried Chicken for the rest of my life. I did not take the offer. I am unbribable at such a low level. It was a joke. I'd have to start at least 10 million. Yeah. No. 10 million for a C minus. Guaranteed C minus. You'll pass the course at 10 million. Oh, 10 million. I think it's 10 million and $50. See, once you get the entry fee after that, it's much smaller graduations. Yeah. So really, it's only an extra 50. So it's fine. Okay. I am going to put you into new groups. Oh, lovely again. Apparently, her dad was one of the founders of Kentucky Fried Chicken. No, she graduated like, I don't know, 8 or 9 years ago. Her dad was Colonel Sanders' Canadian partner. It started apparently as a Canadian company. No, they chose that name apparently. I mean, Colonel Sanders might have been, but it originated apparently in Canada and then spread. I mean, that's just what she told me. She could have been lying. What? I am now interested. Okay, new groups. Find your group. Find your new group. Find your new group. To your new groups. Go. And this one I'm going to give you much less time. Yes. Having the state that's being gaseous. This time the explanation should be much quicker. It was the same. It only should give you a minute. A minute with your group.
Back to
The group. No, when they're just neutral, the same number of protons and electrons. You're making an ion, hence ionization. Yeah. 50 seconds. I want the trend and the explanation. Where's the highest ionization energy? Is the highest ionization energy this way, that way, this way, that way, this way? Say this before. You've got a trend. I want to know what it is. 30 seconds. Sure. You can force force an atom to lose an electron, even if it doesn't want to. So you can take fluorine and you can make +1 fluorine. It is really unhappy, but you can do it. No, it's not really reactive. It'll react with anything around. But you can put it in a container in which it can't react with anything. So yeah, they measure it, and they only do it with small amounts, and then they just measure the amount of force it takes.
So this is kind of okay. I think I understand.
Okay.
Like the trend is like most amount of energy is pumped.
The trend should be exactly the same as electronegativity. Okay, I'm going to start asking groups. Okay, if I can get your attention, Henry. Henry, what is ionization energy? Yeah, don't read it off the board, just what is it? In layman's terms. To get rid of an electron is a great way of putting it. And apparently I wrote this way too wide, so I'm going to do that. Put it back. Okay, another group. Sasha's group. For Sasha. Excellent. Pick either across or up, down. Across. What is the trend in ionization energy across? It increases to the right. Highest ionization energy. If you had decreases to the left, that would also be the same thing. Joffrey, what is the explanation? Why do you have the highest ionization energy to the right? Your group. Okay, whenever we do a cross, there's only one explanation. We always start out exactly the same way. What's increasing as you go across? There's a certain subatomic particle that's increasing. Other one? Protons. So you have an increasing number of protons. What does that do to the attraction to the electron? So what would happen in terms of the force required to take an electron away? More. So increasing ionization energy as you go across. What is the trend up and down a family? Will's group. Just the trend. Where's the highest ionization energy? Going up. And then Donald's group. Why is the highest ionization energy up here? Excellent. Less valence shells, and what is that a fancy word for? What's the fancy word for that? Shielding effect. So there's less shielding effect as you go up. Greater attraction to the electron. Harder to pull that electron away. Richard and Martin, are you guys okay? Okay, do I need to separate you? Okay. Then I don't want silliness, please. Okay. We are now, if I get everybody's attention, we are done trends. I would like you, and I would highly recommend, don't get up and move around yet, make a periodic table. This doesn't have all the trends on it. It has atomic radius, metallic character, but it's missing a couple, like reactivity. Make your own version. Summarize it into one page. For next class. Please don't move just yet. You should do it in your notes in order to study it. Please don't move just yet. Stop moving. Sit down. Sit down where you are. Joshua. I'm asking for people's attention. So when I say Joshua, I don't expect a response. I expect quiet. this assignment that you just did last time on ionization energy, now you should be able to check your answers on the back to see if they make sense, because you now know about the trends. You have to, this is due next day. You didn't get it, then you're getting it now. Yeah. I may not have handed it out in this class. There we go. Graph it. It's on ionization energy. You get actual data. But you still do it. You got one hand? You got a left hand?
I showed this on my writing piece and don't do that.
Oh, no.
Right, you.
What's your name?
I don't know.
Once you have one of these, these are due next day. Start it for prep. And you need one. Not in the afternoon. Tutorials. Yeah, come do tutorials. Next Tuesday, or there are some lunches, but not today. But start working on the head day, work on that sheet, and come see me. Send me an email if you have any problems and you don't know how to start.
And also with the notes, so I just copy and hand it.
Yeah, I'm going to post the notes. We have somebody who's broken their hand, and there's another student who just recently added. If I don't post the notes, you don't see it pop up, just email and remind me. You're welcome. You're welcome.